Talking about Good morning and welcome to webinar 9 in the Building Smart program. Today we'll be talking about hydronic and water distribution systems. This program series is brought to you jointly by Consumers Energy and DTE Energy. Quick fun fact about Consumers: they began in 1886 as the Jackson Electric Light Works. They were started by a gentleman by the name of Samuel Jarvis and the Foote brothers, William and James. Their very first project was installing electric lights in downtown Jackson, Michigan. The second partner bringing this program to you is DTE Energy. They were started in 1849 with the creation of the City of Detroit Gas Company. They were founded by Lemuel Davis, who was an engineer from Philadelphia. And their first project was to provide gas lighting for the downtown Detroit streets and homes. So let's jump into things here. My name is Sonia, and I will be your instructor for today. I hope you walk away from this presentation with a better understanding of the essential components of hydronic distribution systems, how they work together to help provide energy efficient comfort in the home. Here's a rundown of what we'll be talking about. We'll start with the benefits and move into the major components themselves. We'll talk a little bit about materials and equipment options. We'll talk a little bit about some code requirements around the distribution system itself. Then we'll wrap things up with a brief discussion of domestic water systems and combination heating, space heating, and water heating systems. Before we get started here, let's see, we've got a couple of folks in here. So we're going to start with this poll question. John, thank you so much for pulling that up, because the way I've got my screen set up, I can't actually see what's going on in the webinar itself. So thank you so much for pulling that up. Today, I just want a quick question. What's your knowledge level of hydronic distribution systems? So we'll just take a minute to answer that question. Okay, so here are the results. And most of you are somewhat familiar with it, 71%. And then you've got a couple of folks that are very familiar or familiar with it, and then some are not familiar at all. So for many of you, this will kind of be some of you, this will be a refresher. And for a number of you, this will be kind of an introduction or a primer, if you will, on distribution systems. So we're hopefully you find this information valuable today. Let me switch back over to my other screen so I can see the presentation. All right. So often when we think about improving the performance for our HVAC systems, right, whether it's in terms of energy efficiency or the ability to provide comfort, normally we think, oh, okay, I need a new piece of equipment, right? And that's usually some large major equipment in the system. We think that the existing equipment is old, it's outdated, it's not efficient, and so we want what's new in the marketplace. Oftentimes, though, we forget about all the ancillary components that major piece of equipment needs in order to work properly. And often we don't think about the distribution system. We don't think about that as a major piece of the puzzle. And that's unfortunate because it's a piece that significantly impacts the ability of the entire system to deliver comfort and to do that cost effectively. So hopefully after today's session, we'll have a better appreciation for the role the distribution system plays in system performance. And maybe we'll even begin to look at hydronic systems for residential applications, not so much as an old, outdated technology as we tend to think of boilers. They are, quote unquote, in the older homes here in Michigan. Um, but we'll begin to think of them, maybe as contemporary, current, up to date technologies that are and that should be given equal consideration when with forced air systems, right? These are equally viable systems for today's residential market. Um, and don't get me wrong, I'm not necessarily advocating for hydronic systems over forced air systems. One is not necessarily always better than the other. They both have pluses and minuses, um, and they both have their place. So there are applications where one may make more sense and may be the better option, even in with the advancements that we have in technology today. So let's start off talking about a little bit about the benefits of hydronic systems. So, since the primary goal of the HVAC system is human comfort, so let's start there. So the human body is it's giving off heat through a series of thermodynamic processes, right? We sweat when the air around us gets hot or when we exert ourselves. Right now, where each of us is sitting, right, we're in physical contact with things. We're sitting on a chair or a couch, our feet are on the floor. And unless these objects that we're in contact with, are right at the same temperature as our body temperature, 98.6 degrees, or whatever our unique body temperatures may be, we're exchanging a bit of thermal energy with them, right? As we're breathing, we're inhaling air at room temperature. We're heating it up as it makes its way through our respiratory system, and then we exhale it along with a little bit of moisture. When we do that, we're also giving up heat, right? As we move about, right? I'm sitting here talking. I know that you can't see me, but I move my hands when I talk, right? So I am doing that. And as we do that, as we walk around, right, the air around us is moving, and that is also a means of thermal exchange, right? We're giving up energy through convection when we do that to the air. Well, you notice in the chart here that the primary way that we give off heat is through radiation, right? And we're giving off heat to the surrounding surfaces, right? The walls, the floor, the ceiling, the windows in the room that we're in, the bookcase across the room, the computer that's sitting in front of us, right? And one of the interesting things about the hydronic system, right, is that it also operates largely through radiation. Now, it can use forced air as well, and we'll talk a little bit about that later. But the most common hydronic system is using radiation as its primary means of heat transfer, right? In contrast to a forced air system that heats up the air and then moves that air around the house, right? The hydronic systems are using radiators and sometimes convectors as well, that radiate heat to those surrounding surfaces. Those surfaces then reflect that heat back into the space, and to the occupants in the space to maintain comfort conditions. Now, it's worth noting that, you know, we would not be comfortable in spaces just because the air temperature is at 70 degrees, which is most people think is the ideal temperature, right? Um, but just because the air is at that temperature, if the walls or the windows or the floor were at say 60 or 55, we would be uncomfortable, right? And that's because the mean radiant temperature of the space, right, of the home is just as important as that air temperature, right? And the hydronic systems help address that. So in some ways, they can provide a more comfortable, more even heat, um, than forced air systems. Um, Now, for a number of reasons, homes with hydronic systems tend, but not always, they tend to be or tend to use a little bit less energy than homes with forced air systems. A couple of reasons for this is when forced air systems are operating, they cause changes in home pressurization, which can force conditioned air, right, heated air, out through the cracks and crevices, small holes in the building envelope. And then, of course, depending on the location of the supply outlets and the return grills, Forced air systems can have more of a floor to ceiling air stratification, right? We talked a little bit about this last week's session. Those higher temperatures near the ceiling, you're gonna see higher thermal losses occurring with that, right? So a less efficient overall system. Some of the energy savings with hydronic systems also comes from the fact, or I guess that with hydronic systems, you don't have those potential for air pressure differentials, so you don't have those leaks. And that helps to improve the system efficiency. Another way that the system efficiency is improved with hydronic systems is through the concept of distribution system efficiency. Energy savings can come from the fact that, well, let's back up a little bit. So the distribution system efficiency is the ratio of the amount of heating delivered by the distribution system to the amount of electrical energy input required to get that heat where it needs to be, right? So basically, for your hydronic system, it's looking at the amount of heat that you're putting out compared to the pump energy, right, that you're expending or that's required to get that heat where it needs to be. And that pump energy is based on the volume of water, on the length of the piping, on the fittings that are in the piping, the height of the piping, the location of the radiators. All of that goes into developing the power requirement for those pumps. This is similar to an air distribution system, right? That would be looking at the heat output and the amount of fan energy that's needed to get that air around the building, right? And so the units of the distribution system efficiency are BTU per watt per hour, right? Now, to distribute the same amount of energy, pump watts may be on the order of 10% of what a forced air system might require, right? So you've got significant distribution system efficiency there with the hydronic system. And that's largely because water has a higher specific heat than air. So as a heat transfer fluid, a pound of water has a heat carrying capacity that is, more than 4 times that of a pound of air. But of course, when we're talking about heat transfer, we don't talk in terms of weight, right? We don't talk in terms of pounds of fluid. We talk in terms of volume. You got cubic feet for air, gallons for water. And so, considering the density of both of those fluids, volume for volume, water has a heat carrying capacity that's roughly 3,400 times that of air, right? So, if you had a cubic foot of air and converting gallons into cubic feet, the same volume, right? Cubic foot of water, right? The water would have a carrying capacity of 3,400 times that of the air. So this means that the material that conveys the water, that piping, right, can be a lot smaller than the ductwork that has to convey that air because we need a lot less water, right? So there's right there some additional savings, right? You've got material first cost and labor installation costs, right? So there you've got some savings in that, particularly on the material side, right? When we look at the first cost for ductwork, it's usually about twice the cost of copper piping, 13 times the cost of PEX on a per foot basis, right? And additionally, that tubing doesn't take up nearly as much space as the ductwork, right? So for the same temperature differential, for example, between the working fluid, either the air or the water, and the ambient air, right? The air system would have a greater heat loss, right? Because it's got greater surface area, right? And it's going to require more insulation. That's going to be adding additional cost to the project. Hydronic systems may also be a little bit more flexible than forced air systems because they can serve multiple loads, right? So they can serve pool heating and snow melt systems with the same equipment. This reduces the required installation cost because now you don't need multiple heating sources. You don't need a boiler for space heating, a separate boiler for snow melt, a separate boiler or a separate pool heater, right? That can all just be one piece of equipment. That means you also don't have to have multiple fuel lines, multiple gas lines. All those individual pieces of equipment don't have to be piped. You don't have to have the electrical connections. You don't have to have multiple exhaust systems. So now you're saving on first cost in terms of equipment and material, but you're also saving on labor, right? Because all you have to do is extend the distribution network, right? Sometimes hydronic systems can even be combined with a forced air system. We'll talk a little bit about this later with what we call either a fan coil or an air handler. On the commercial side, sometimes it may be referred to as a water furnace on the residential side. All right. And because they're not moving that air around the home, right? Hydronic systems are also not moving airborne particles around the home, things like dust, pollen, like microorganisms, right? So the hydronic systems tend to be a better choice for homeowners with respiratory issues, right? Folks with asthma, folks with allergies. So for those of you that are architects and builders, these are some of the things that you want to, discuss. Comfort, energy savings, design flexibility, cleaner, quiet operation. These are the things that you want to discuss with your homeowner clients as they're contemplating what type of system to put in their new home. Right? Oftentimes, we just automatically go to the forced air system, but there may be reasons why, for a particular homeowner, a hydronic system is better. All right. So now let's take a look at the basic distribution system. The heart of the system is the heating source, right? The boiler itself. And so like the forced air furnace, this typically generates heat by burning a gas, but it could be, an electric system as well. So it doesn't necessarily have to be gas, but most of them are. Um, and instead of imparting that heat to air, it's imparted to water this time, which is circulated around through a piping system. There's a small pump instead of a fan that you would have with your furnace. And that water then flows to, instead of flowing to outlets as you would with a forced air system, we flow to what we call emitters, right? And it enters at one temperature and it leaves at a lower temperature as it gives up heat to the surfaces and to the space, right? Usually that delta T is about 20 degrees is generally what we design for, but that's kind of an old rule of thumb, and we can actually go with a higher delta T there on across that boiler, and that would improve the efficiency of our system. It might even make, allow us to install smaller piping as well, which would reduce costs, right? So to that basic system, right, we add a couple of controls, right? One of the first things we add is a centrally located thermostat. This is going to be somewhere within the house, and this is going to tell the boiler when to turn on, right, based on its set point, right, based on that space set point. There's a temperature controller for the boiler itself, for the water in the boiler, right? And this modulates the burners, right, to make sure that the water temperature in the boiler stays between its set point and its preset differential. Usually it's about 10 degrees. So if the boiler set point is for 160, at 150, the burners would come on. If the water temperature in the boiler is between 150 and 160, the boilers would be cycled off, right? So we want to keep the boiler on so that it's ready to go whenever we do need whenever there is a call for heat, but we can cycle those burners on and off so that we don't overheat that water, right? This would also control the pump and turn it on as well, right? So the next component is the expansion tank. So as water heats, it expands, right? Those molecules get a little bit bigger and it takes up more space. This would increase pressure within our system, and we don't want to do that because we've got a closed loop, right? This is all steel and metal, right? We've got it designed for a particular pressure. So it can go a little bit lower, but we don't want it to go higher, right? So for the tank, the expansion tank itself, one side of it is a volume of air that is that's contained, right, in a diaphragm, and the other side of it is open to be able to accept the heated water that's expanded in volume, right? And so as the water enters the tank, the air volume gets depressed. Now, the the way the tank is set up, no water or no significant volume of water enters the tank until it's heated, right? And so one of the things that we want to make sure that we do with this tank is we want to make sure that it is properly sized for the system, right? So we're going to size that tank based on the air side pressure, based on the density of the cold water and the distance from the tank to the top of the system, right? And there's a formula for that. And there's also a 5 psi allowance, right? So in case there's any extra, there's some wiggle room there, right? Um, and that 5 psi allowance allows the boiler relief valve to get about 5 psi lower than the rated operating pressure when the system is at maximum, when it's at its maximum operating temperature. Now, often tanks are preset or pre-pressurized by the manufacturer to 12 psi. That's a pretty common numbers, and oftentimes installers may think, okay, that's close enough to what it's normally going to be for a house with 3 stories, including the basement where the boiler typically is. But we actually should adjust that air pressurization, right? It should be adjusted to the actual calculated value based on the actual job site conditions, right? So this makes sure if by doing that, we are assured that the diaphragm will be fully expanded when the system is filled, but not heated. Um, and so if we don't do that, then the diaphragm would be partially compressed before the heating started, and the full tank volume would not be available when things did begin to heat up, right? And in which case, the tank may cause the relief valve to open every time the system heated up, right? Because it would be a smaller volume in there, and that's not what we want. So we want to make sure that we do properly size those expansion tanks. And just a quick note about expansion tanks. Very often the tank is marked with an acceptance volume. This is not um, the calculated minimum tank volume, right? This acceptance volume is the volume that the tank will accept for a given change in pressure. That the calculated minimum volume of the tank is the size the tank needs to be for the system, right? When we install these tanks, we want to make sure that they're well supported, that they're installed vertically. We want to make sure that there's no air bubbles that are getting caught up under the diaphragm if it's installed upside down. Um, and we want to make sure that it is close to the boiler, right? So, which allows a faster response time, minimizes pressure fluctuations. We want to make sure that it's before the pump. In residential applications, the pump is typically, it may be called a circulator, but it's a small pump, right? And we want to make sure that the expansion tank is installed on the suction side of that pump, where the water's drawn in. This helps prevent the pump from cavitating, right? And it helps ensure we've got proper air removal. Um, and another quick note about the expansion tank, an old rule of thumb was that it was always installed on the cold water side. And when we look at the water heaters, we'll see that it is installed on the cold water side there. This was done in the past. This was done to accommodate low pressure drop boilers and oversized piping sometimes. This can still be done as long as it's close to the pump. But it should not. But it shouldn't necessarily be done when there's a significant pressure drop between the point of no pressure change, which is where we've installed the tank, and the pump inlet, right? So there's a significant pressure drop there. We want to make sure that that the tank is installed, closer to that pump. So and in the drawing there, you can see that the tank is actually on the hot water side, not on the return water side. The next component to talk about is the pressure relief valve. As that water gets hotter, right, it expands. That's why we've got the expansion tank. As that system pressure increases, it could potentially exceed the pressure rating of some of the components. Which would cause a failure. Boilers. People have said, boilers are. I don't necessarily like saying this, but they're kind of like a bomb, right? They're pressurized systems, so it could, if you had a catastrophic failure, that would be an explosion, right? That's what that would be. And so we want to make sure that we've got a lot of safeties in these systems to prevent that from happening. Right. So we want to make sure that we've got a relief valve that's located close to, if not actually on the boiler. Right. And it has to, this is one of the code requirements for boiler systems. We want to make sure that it's installed in the upright position, in the vertical position, so that there's no potential for dirt or anything that could inhibit its action. Right, keep it from properly seating, and that might potentially allow a leak. We also want to make sure that the pressure relief valve is piped with minimal turns, and that there are no valves or anything to interfere with its operation, no valves between it and the boiler, and nothing between it and its termination. We want it to terminate either into a waste receptacle or to a floor drain. We actually don't want it to go directly to the drain, though. We want to have it about 6 inches up off the floor, just in case anything happens. You might get a clogged drain or something, and so you don't want that to hinder or hamper the operation of this valve. So you want to have free flow. So you're going to terminate that about 6 inches above the floor. Because there are minor losses in hydronic systems, the valve packing, pump seals, air vents, et cetera, you're getting a little bit of evaporation of that water. And so you've got to make that water up. So we have a makeup water system. And that system consists of some valves. It's got a pressure reducing valve / feed water valve. Right, that's because the municipal pressure is likely higher than the relief valve setting. And so we want to be able to allow water in when the outlet pressure drops below that set point. So for example, when air is vented out of the system during service or startup, we want to be able to allow that to be expelled. The makeup water system also includes a backflow preventer. This does exactly what the name says, right? It stops the water that's now in your system from flowing back into the municipal potable water system, right? Because the water that the municipality is sending to your house, they don't know if you're using it for a boiler or for a shower or for making iced tea, right? So you've got potable water coming to the home. And now you're using it in this system, which is a closed system, but it may have some sediment in there. There may be some residue in there. There may be some contaminants in there that you don't want going back out to the city system or to the municipal system, right? So you're gonna have a backflow preventer there. You're gonna have some pressure. You're gonna have a pressure gauge there. You're gonna have a shutoff to allow for isolation. You may have a fill valve there to speed up fill, right? To have it fill a little bit faster. And then you're going to have a purge valve, right? That's going to also get rid of air in the system. There's a check valve there. Older systems may have a weighted plug that had that the mechanism had to be lifted in order to operate the valve. So you may still see this in some older applications in some older homes throughout the state, but newer systems tend to have a spring-loaded check valve, and this helps to prevent what we call thermal siphoning, which happens because of the. Excuse me, 1 second. I get a drink of water. Thermal siphoning. This happens because of the difference in density between the cold return water and the supply, the hot water supply. Right, so because of that difference in density, you may get what we call thermal siphoning. where the heat may drift when the boiler is not functioning. The heat may drift over into the emitters, and so we're going to stop that. We've got a check valve that stops that hot water from flowing, right? Because that's an undesirable situation. There are times when we do design thermal siphoning into systems, but in this particular case, it's not something that we want to have happening here. So we're going to have a valve there to prevent it. And then lastly, for the major components of the system is the air separator. And this is a device that kind of looks like an expansion tank, but it's skinnier. And it creates a low pressure region so that air and other gases, oxygen and two that may be in the system, because they're at that lower pressure in this tank, they will flash, right? They'll bubble up, and then those bubbles are then collected into a chamber and then expelled through an auto vent that's typically at the bottom of the air separator. And so we want this air separator to be located at the highest point of temperature in the system, which is typically going to be right after the boiler, right? So now that we've talked a little bit about the major components of the system, let's talk a little bit about piping arrangements and how the pipe is laid out in the system. So typically piping falls into one of two categories, either series or parallel, which are similar to how we define series and parallel circuits for electrical circuits, right? So in a series circuit, you've got every component is water flows through all of the components in series, right? And so these systems tend to be simple and low cost. They're great for really small homes. And again, there's a single flow rate, right? There's a single flow rate through all the piping and through all the emitters. The pressure drop here for this system is the sum of the pressure drops across each of those individual pipes. Some of the downsides of this system are that one, the big thing is that water temperature decreases as it flows through each emitter. So emitter 3 doesn't see the same temperature, the water temperature, as emitter 1. That means that the individual emitters need to be sized based on the temperature that they will encounter. Very often installers will average the water temperature and size the emitters based on that. That can lead to oversizing at the first emitter and potentially undersizing at the last emitter, which means that spaces in the house will be under or overheated, and then there will be spaces that won't necessarily be comfortable, right? So the other downside to this system is that you can see it, since water's flowing through all of the emitters, you can't turn anything off, right? There's no zoning, there's no independent control of any single emitter, right? You can't even regulate a single emitter because that's going to impact everything else downstream, right? So everything is on, everything is open, right, all of the time. So this may be okay for some systems, for again smaller homes where there's traditionally one zone, and historically most homes have been treated as a single zone anyway. But we are now beginning to recognize the value of zoning in homes. So second floor may not necessarily be maintained to the same temperatures as the first floor, right? Or rooms where people gather often, may be held at different temperatures, right? Or the kitchen where you're going to be cooking and adding heat, that may be zoned for different temperatures, right? But you can't do any of that with this series circuit. So a slight change to this circuit is what we call a one pipe series arrangement. And here you can see that we've got a little bit of branch circuiting, right? So now you don't have just this one set of pipe here with all of the emitters on that, they actually have little branches off, right? There's a T, right? And then there's a valve there. So this is still a simple and low cost system, but now we've got some valves, so we can regulate, we can control, right? We can zone. We can even have emitters that are different sizes if we want, right? We may, for example, you know, let's say we want the bathroom emitter to be, you know, larger than it necessarily has to be, because we want to be able to heat up that bathroom quickly when we go in to take a shower or take a bath, right? So we have that kind of flexibility here. The pressure drop is still the pressure drop across the sum of, you know, all of the components. The downside to this is you still have that water that's flowing through, to a degree, through each emitter, even though, you know, the water has an option, right? It can go this way here, or it can go this way here. When it comes back to this point and gets mixed here, right? It's going to be a mix of this temperature that was at this point and the temperature that it was coming out of this emitter. So this temperature is going to be lower than that temperature. And that's the temperature that's coming around here to this next emitter, right? So you still have that issue. And so you want to make sure that when you have a system like this, and this is fairly common for residential systems, you want to make sure that the emitters have been properly sized for their location in the system and the water temperatures that they're actually going to be seeing, right? And a system like this is good for, you know, systems that use fin tube or panel radiators, or if they use fan coil convectors, it's pretty good. And we can see here that the system looks pretty much the same as, in, you know, other than the branches here, it looks pretty much the same as the series system. But this is best with what we call a primary, secondary piping system. So where the boiler is hydraulically isolated. And so here we would have, there'd be constant circulation around that main circuit called the secondary loop, which is this loop here, right, where we have our emitters. And then the boiler and the boiler pump, right, the boiler pump here that we've added, right, would only be running when the boiler's operating, right? So that helps to, you know, to improve energy efficiency and helps also to reduce losses from the boiler cycling. Now, in the drawing here, this is for just for visual purposes, and so so the length of this piece of pipe here may seem to be longer than what it would typically be in practice. Typically, we would really want this to be, for a system like this, 6 inches or less, right? We want this to be a very short pipe here. We're just trying to hydraulically isolate this here so that we can have continuous flow around here, right? That allows us to, you know, achieve better comfort conditions in the home. The multi-zone, multi-circuit system. Here we can see that we've got branch piping, right? So here we have a separate circuit for each zone, and you can do this a couple of different ways. The drawing here, the image here shows it with separate pumps. It could also be with a single large pump and individual zone valves, right? But the individual pumps, the separate pumps are better because you've got, because you have the individual pumps and not one large pump, those individual pumps are going to be smaller, so they're going to use less energy. They're only going to operate when their zone, when their branch, right, is calling for heating. If you have a failure of a pump, you only have an impact to that particular zone. The entire system is not shut down. Right? And additionally, if you've got a single large pump, when you only have one zone, for example, calling for heating, you may have a little too much flow, or you may have a little too much noise, right, in the system. Right? So those are just detractors from homeowner comfort. But then the nice thing about this is that each zone gets about really close to the same incoming temperatures. So that generally means that the emitters can be smaller, and the temperatures of the system, the temperatures of the water in the distribution system may actually be lower, and this may improve overall system efficiencies. Um, it's not necessarily a con, but something to think about here. You've got to have a check valve in each branch so that there's no flow when a circuit is not in use. Um, and you may still have in a particular branch, right? This branch has just one emitter, but this one here has two, right? And so in that particular branch, you still may have water flowing from one emitter to another emitter, and right, so that second emitter, will not have the same incoming in temperature as the first emitter, right? So again, you've got to make sure that the emitters are sized for their location in the system. Um, so those were the series pumping arrangements. We also have a parallel piping arrangement. And with parallel piping, this is more common in commercial systems, but I'll talk about it just because sometimes we do see this in large residential, multifamily residential, we may see this there. And so for the parallel piping systems, you've got two major divisions, direct return and reverse return. Um, Now, in these systems, there's a common supply and a common return, and you can see here that with the direct return, the hot water comes into the first emitter and then immediately comes back to that return line and goes back to the boiler, right? So, um, and then you've got water coming to the second emitter here, right? And then coming back immediately to the boiler. So the nice thing about the parallel system is that each emitter gets the same water temperature. So they tend to be smaller, right? But you have some issues with balance, right? So with the direct system here, you can see that the first emitter is closest, to the system, to the pump, to the boiler, what have you. And the distance between adjacent branches could vary significantly, right? This could cause significant, high head losses, which, need to be accounted for when we design the system, right? Also, for the last emitter, it's farthest from the pump, so it may have a lower flow, right? That lower flow is going to be less heat output, right? So this too needs to be accounted for in the design. You can do that with some balancing valves that that can correct for that, or right, we can use the reverse return system. So here, the branch that's close to the pump on the supply side is farthest from the pump on the return side, and vice versa, right? So this helps to correct that flow and balance. But even with that, there are some other differences with this system. So, for example, the piping for the reverse return system. On the supply side, the pipe gets smaller the farther away from the pump you get. You want to make sure that you have accounted for that. On the return side, the pipe gets bigger, right, as you come back. I want to make sure that for both of those, we're designing that pipe, we're modulating that pipe size to kind of maintain a head loss of about 4 feet per 100 feet of pipe through there, right? These systems also tend to have a lower overall pressure drop across the boiler. So again, boilers traditionally designed for 20. They don't have to be 20. You could have a greater pressure drop. But when you do this piping system, the parallel circuit, you may tend to, instead of seeing 20, you may see only 10, right? But again, you want to try to go for higher pressure drops that lowers or decreases the size of the piping and improves overall efficiency. All right. So when we look at piping materials, we want to make sure that the materials that we use are suitable for the application. There are code requirements for that. Right. This is just an excerpt of what some of those might be. There's a complete table in the Michigan Residential Code that looks at what materials are used and how they can be used, what temperatures they can be used, where they can be used, what types of systems they can be used for. But we want to make sure that we're adhering to that. Very interestingly, I thought this was really kind of interesting. Used pipe and fittings can be employed in a new system, as long as they're free, as long as they're clean. There's no debris, there's no foreign materials, except with ground source heat pump piping. Those have to be brand spanking new. But otherwise, we can actually use used materials, which may come in handy, particularly now when costs are so high. Um, we want to make sure that our piping system is adequately supported. We want to make sure that the supports are compatible materials with the pipe itself. We want to make sure that there are well, that we don't exceed the maximum interval spacing for those supports, so that we don't have any sagging or bending. We don't want the pipes to be moving excessively, because this could cause leaks or failures. We also don't want to cause any, these thermal stresses can also reduce the life of the piping, right? Or make the pipe require additional maintenance, and we don't want to do those things. So we want to make sure that they're supported properly with compatible materials, at proper interval spacing. And in addition to the piping being supported, for baseboard convectors in particular, we want to make sure that they are supported, and that's independent of the pipe, right? So here we can see that pipes are supported. We've got supports that are suspended from joists, and we want to make sure when we've got those baseboard convectors that those are supported independent of the piping, right? So that means attached to the wall or something there. There are many types of convectors and radiators that could be used for the system. We want to make sure that we match those emitters to the system. Some are well suited to systems with certain traits, with higher temperatures or lower temperatures. For example, if you've got low temperature system, 90-degree water, 120-degree water, that's okay for radiant slabs and floor systems, but it's not okay for fan coil convectors or radiant panel heaters, right? Or for fin tube, right? For fin tube, for example, we want to use that is best suited to higher temperature systems. So 160 degrees to 200 degrees, right? That's also great for the radiant baseboard. There are many code requirements for these systems. And we'll talk a little bit about some of those criteria now. One of the biggest things, though, is test pressure. These piping systems need to be hydrostatically tested to make sure that the piping can withstand the pressures expected in the system, and then pressures in excess of what's expected in the system to provide additional assurance against catastrophic failure. Right, so in general, we're going to be testing at pressures that are 1.5 times the maximum design pressure, and we're going to pressurize that pipe, and then we're going to hold that pressure for between 15 and 20 minutes, and we want to make sure that there are no leaks, and if there are any leaks, we're going to repair them. The pressures differ for example, for radiant floor system or for a ground source heat pump system. There we want the test pressure to be 100 psi. Actually, for the general system, it's either 1.5 times the maximum design pressure or 100 psi, whichever is less, and for a residential system. But for radiant flooring and ground source heat pumps, we're going to hold that pressure for 30 minutes, right? And then if the flow rate changes, in the system, that tells us that there's a leak. If there's a change in the pressure, that tells us that there's a leak. And if we have either a flow rate or a delta P differential of more than 10%, then we're going to take some corrective action, right? We're going to fix that. We're going to go back and test again. Right. So when we've got on the mechanical side, we want to have some insulation around that piping, right? This is going to help to maintain water temperature and reduce heat losses, which could have a negative impact on the energy efficiency of the system, right? So if we've got fluid that's being transported and it's above 105 degrees, which it would be for a heating system, right, it's going to be insulated to R3, right? If that were a slab on grate, though, for a radiant floor, which would be a thin slab, we would be using R5 for that. If it was a suspended floor, we'd be using R11 in the joist cavity. There are a number of valves that are required, right? So these valves are going to open and close to either modulate or start or stop flow in a particular situation. So we've got shut-off valves, right? These are installed in the supply and the return. They're installed on both sides of pressure-reducing valves. They're installed at all at the major equipment. So at the boiler itself, they're not installed at the pumps or air separators, but they're installed there at the boiler itself. And this is to be able to shut off or isolate the equipment for service, for replacement, or if there's any type of problem. Right, we're going to have some pressure relief valves. These are going to be on the low side of the system that's been reduced in pressure. You're going to have backflow prevention. You're going to have some safety devices to prevent overpressurization situations. We're also going to have some controls and instrumentation on these boilers, right? We're going to have low water cutouts, right? This is another safety device, right? This automatically shuts off the boiler if the water level drops below the operating level, right? So that the boiler doesn't dry fire, right? You're going to have, a pressure gauge, right? This is going to indicate the pressure inside the boiler. It's going to help the operator, in this case the homeowner, be able to monitor what that operating pressure is and make sure that it is at a safe and efficient level. You're going to have some temperature gauges, right, so that we know what the water temperature is inside the boiler system, so that the homeowner can know that this water temperature is in the right range. If the temperature gets too high, right, we can see that, right, and this also impacts the energy efficiency of the system. Right. That expansion tank, we talked about this a little bit earlier. So there's for larger multifamily residential, right, where it would be considered a commercial application, right? There's a formula for determining what that minimum tank volume is going to be. On the residential side, right, there's just a really handy dandy table that tells you here's what your system volume is, and here's what your here's your minimum tank capacity, right? So that's a tabulated value. For larger systems, again, multifamily systems, you may have an open type tank. This is an older technology that we've seen in older facilities, but there are criteria. We may still have applications for that, or you may run into these in some older homes, and so we have some code criteria regarding those. But the metrics that we're looking for, I want to talk a bit about that. In terms of the boilers, right? The old way of thinking was looking at really the boiler efficiency and the boiler turn down, looking at the piece of equipment itself, right? Our new way of thinking, right? We want to look at things like the hours per cycle that the boiler is operating. We want to look at the optimal flow rate for the boiler. We want to look at higher temperature differentials for that boiler. And we want to look at distribution efficiency. So we want to begin thinking about other things as opposed to just the boiler's turn down and just the boiler efficiency. When we look at the overall system performance, right? We want those boilers to be running longer, right? We don't want the boiler to have a lot of starts and stops. So that hours per cycle, that's a important number. Right? We want it to be bigger than it has been in the past, right? Because the boilers are operating more efficiently when they're operating at their steady state point. All right, some targets that we have for that distribution system. We want to make sure that we've got turbulent flow, right? We want that turbulent flow so that we've got good temperature mixing. We don't want laminar flow. Like if we're looking at ductwork, we might want laminar flow because we want smooth duct flow. We want airflow. We don't want a lot of noise and things like that. But with hydronic systems, we want that turbulent flow because we want that good temperature mixing. We also want to design for flow rates between 2 and 4 feet per second through the system. And we want the hours per cycle to be greater than 2, right? Bigger is better in this particular case. But we want it to be definitely greater than 2. And we want that temperature differential, again, we want that to be higher as practical. When we talk about domestic water systems, here's just an example of what a typical system might look like. And here, we want to make sure that we're following the manufacturer's instructions, right? For what this for the components that we add here. So we're going to have a drain valve that's going to be at the bottom of the tank. We want to see here that we've got a um, a drain pan for the tank, right? That drain pan is going to be an inch and a half deep, right? And it's going to be fabricated of either galvanized steel or aluminum or plastic. For electric water heaters, for gas water heaters, only galvanized or aluminum is acceptable. And we want that drain pan to terminate over either a floor drain or to the outside. We want to have some pressure and temperature relief valves. They can either be separate or they can be combined. If this water heater is used for space heating, then we want to make sure that it's got a master thermostatic mixing valve, right? An anti-scald valve, if you will, to make sure that the temperature that is sent, the temperature of water that's sent to the domestic purposes within the home is less than 140 degrees. The same criteria apply for shut-off valves. We don't want a shut-off valve, between the relief valve and the valve termination. We don't want a valve, but anything between the relief and the tank or between the relief and the equipment that would hinder its operation, right? And similar to boilers, we want those relief valves to terminate off the finished floor. So right, not directly into the drain, but about 4 inches higher above that, so that it has free flow. We want our domestic water piping to also be insulated, similar to the hydronic system. And the insulation will vary depending on whether or not there is a on-demand or non-demand recirculating system, right? So if there's a recirculating system, but it's non-demand based, right, then the insulation needs to be R3. If it is demand based, then the insulation can be R2. We want to limit the length of domestic hot water pipe runs, right? This is for faster water delivery and for energy conservation. And the code has some information, some maximum limitations on that based on the diameter of the pipe. Yeah. This is a criteria on the commercial side, not necessarily for the residential side just yet, but it's still a good idea. Heat traps help improve the efficiency of the system and reduce wasted energy. They minimize heat losses. They just like the check valve in the hydronic system. They prevent that sort of thermal siphoning, right? And so newer water heaters often come with these already installed, but they can be added to existing systems. Sometimes you'll see older existing systems that had this loop in the piping. That's a form of heat trap, right? But newer systems will have these valves here installed, and they're color coded so you can tell which one goes on the cold side, which one goes on the hot side, and you can see the color coding here on the unit as well. There are code requirements for lots of other things, including heat trace systems, recirculation systems. If you've got drain water, heat recovery, there are code requirements for all of that. I want to talk briefly now about, and we're coming up on the end of the presentation, I want to talk real briefly about combined systems. So they can reduce infrastructure costs, right? Again, we talked about this. You got fewer gas lines, fewer exhaust vents. There's the reduced space requirements, and they can also help you save energy, right? So with these systems, you typically have a high efficiency heat source. So you've got a water heater or a boiler. You could have a storage tank water heater. You could have a ground source heat pump unit, or you could have a heat pump water heater, right? These things also can be combined with any of the emitters that we've previously talked about, right? One of the things that we haven't talked about, though, is the hydronic furnace or the water furnace or the air handler in what we would call it in commercial spaces, right? But here you can see here in this photo here where we could have a gas water heater, if you will, that is sending hot water over to this fan coil unit. And this fan coil unit is just like a furnace when you look inside, right? It's got a blower, it's got the control board, it's got the insulation that you see. It's got all it's very much like a furnace, right? You've got your two compartments, but instead of having a heat exchanger, right, where you're burning combustion or where you're burning natural gas to generate heat, here you have a hot water coil, right? So you're taking hot water and you're sending that over there. You're blowing the air over that hot water. So it's very similar to a furnace, to a forced air furnace system. Um, and it is a forced air system. It's just not using a furnace, right? So, um, yeah. So when you have a combination system, you want to make sure that you're following the local codes, national and local codes. You want to make sure also that you follow the manufacturer's instructions for how to install that piping distribution system. You want to make sure that you appropriately size the pipe and the fittings. You definitely want to make sure that you include backflow prevention, and that you've got those balancing valves, right, in that system. Oftentimes, when you have a combination system, you may have to go through an optimization process, right? This is going to be an iterative process. It's going to take a look at adjusting the temperature of the water, the water heater set point, the water circulation rate, and the airflow rate, right? To make sure that you've got all those um, metrics at their most ideal point for optimal system performance, right? This is just the steps that you might go through for that iterative process. So as an example here, and I'm going to go over a little bit, I'm going to probably go over about 5 minutes. So if you could bear with me, I really appreciate it. And so here just is an example of what can be achieved with system optimization. So here, this system happens to be rated for potable use. So it's mixing domestic and space water heating. And in this particular case, the initial system was designed for the design load was 40 MBH, but the system was set up to give out as much heat as possible with the air handler at the highest speed. And here, with going through that iterative optimization process, we were able to lower the the lower GPM, um, and provide at about a 10% efficiency gain for the system. We were able to lower the set point. We were able to reduce the airflow and still provide a supply air temperature that's acceptable for comfort in the system. And we can see here now that the output matches the demand a little bit better. Let me go back a little bit, right? The output actually matches the demand. So instead of being oversized, the system being oversized, right? Now it's actually matching the demand. So our costs are going to be less. And what's coming up next in the future for boilers, right? We're on that. We're ushering in that era of smart boilers, right? Smart boilers and thermostats and smart systems. And we'll be talking a little bit about smart systems in an upcoming webinar. But I just want to mention with hydronic systems, right? Smart systems allow you to do room by room control. They allow you to do zoning and more efficiently. They can be used with remote control, so you can control them from an app from your phone. There are things I want to tell you now, but I'm going to wait until the till we start talking about smart controls. And with that, I'm going to stop and take any questions. And while we're waiting to see if there are any questions, I'll let you know about the upcoming webinar. So the next webinar in our series is next week, Tuesday at this same time, 11 a.m. And we're going to be talking about mechanical ventilation. So we'll talk about whole house and local exhaust. And with that, I'm just going to put the thank you slide up here, and I will turn my camera on. And if there are any questions, I will uh, take that. So I'm going to stop sharing now and we'll just kind of pause. Okay. I don't see any questions, so we'll go ahead and we will close out for today. And we look forward to seeing you next week, where we'll be talking about whole house ventilation. Thank you so much. Everybody, have a great day.